in an attempt to answer the question as to the capabilities of the Dreadnoughtus, and more specifically, the function of the chevron on the creature's tail. A scale model was developed which would allow for an investigation into the forces and constraints at play.
Tail movement can be estimated as an arrangement of elastically connected compound pendulums. We began the construction of a mechanical model based on skeletal and muscle estimations, limited to 1 degree of freedom. This was accomplished through the manufacturing of CNC aluminum vertebrae with widely adjustable muscle connection points and sensor mounts. The links are interconnected with bronze bushings, nylon thrust washers, and spring-back mechanisms, including both torsion springs and a rigid Delrin rod held in place with 3D printed guides. These measures were taken to provide a tail swing similar to that of the Dreadnoughtus.
The base and tail mount of the test fixture were constructed out of plywood, allowing the tail to be screwed onto the mount. 80-20 aluminum rails were then fastened onto the base of the test fixture to allow for the force plate to be attached and adjusted as necessary.
2 force plates are mounted on 80-20 structures of a test fixture by solder screws. An impact sensor is mounted on the force plate, and the tail could swing and hit on the other plate, so that the team could connect data about tail movement from the sensor.
Accelerometers, flex sensors, and force sensors were added to the tail in order to measure and ensure that the forces exerted on and by the tail are reasonable. Through hand calculations, we learned that an accurately scaled dinosaur bone would be able to withstand 1,500 pounds of force, far more than our prototype can manage.
The robotic model of the tail and data acquisition is controlled through a graphical user interface, or GUI. The GUI is built with processing and IDE for Arduino GUI development, and displays the input from the user and interprets signal from processing to Arduino using USB serial communication.
Electrical solenoids and steel cables replace muscles and tendons. As similarly to muscles, solenoids pull with an increasing force as the distance remaining reduces. The contraction of the solenoids results in whip-like movements of the aluminum links, demonstrating what Dreadnoughtus might have been capable of.